So, assalamu alaikum. Hi, everyone. This is Abdullah from Reservoir Solutions team. Welcome to our webinar today. I will do 5 minutes presentation about Reservoir Solution. Then, hi, everyone. Reservoir Solutions team. Welcome to our webinar today. So I will do a 5 minutes presentation about Reservoir Solution. Then Mr. Chris will do his presentation. So first, about Reservoir Solutions. Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researches like PhD and master degrees. We are also assisting in writing technical papers and publish it. Also, we are providing technical petroleum courses by industry experts. Also, we are providing mentorship programs. Before starting talking about our webinar today, I just wanted to introduce the 2 upcoming courses into our company. We have 2 upcoming courses on the 5th of June. The first course is well killing methods, that it will be 5 or 4 intensive days about well killing methods. We will introduce several methods for how to kill your well and do the safe operation. We will provide the link to overview the course content, and also if you wanted to register into that course, you can register from the provided links into the Zoom chat. The second course, it will be the practical seismic interpretation. This course, we will use the software to do practical interpretation for the seismic data, 2D and 3D. It will be 5 days, 5 intensive days for how to interpret your seismic data to pick the horizons and faults for the reservoir. If you wanted to enroll into that course, you will have the link provided into the Zoom chat to register for this course. About our webinar today, it will be done by Mr. Chris Fletcher. Mr. Chris Fletcher graduated from Louisiana State University in 1978 with BSc into geology. He was open hole wireline field engineer for Atlas in Gulf of Mexico and Rocky Mountain regions. Also, MWD and LWD field engineer for Baker Hughes in Gulf of Mexico, Central Asia, and also in Middle East. Prospect generating geologist for Texas Oil and Gas in Gulf of Mexico. Also, he is doing consulting operations geologist in Caspian Sea, Russia, Central Asia, and West Africa. Consulting geology specializing into pore pressure and fracture gradient modeling in Gulf of Mexico, Eastern Europe, and Central Asia, Africa, and also in Brazil. He is member of global drilling staff for responsible for approval of all BBFG products globally. Also, he is currently consulting with Scoop Tech LLC located in Cornell in Texas. The webinar rules, please ask your questions into the Zoom chat, mute your microphone and camera. In case that you wanted to have a certificate of attendance for this course or that webinar, you can fill into the form that its link will be sent into the Zoom chat. Also, join our Telegram channel for upcoming courses and webinars, and also we will provide our contacts into the Zoom chat. Thanks all, and Mr. Chris, you can start your presentation.
Thank you for that introduction. I want to thank Reservoir Solutions and all the attendees for the time you are giving to this presentation. Please feel free to take any notes and reserve your questions for the end. With that said, let us begin.
Okay.
My specialty is pore pressure and fracture gradients. This is a very nebulous subject. Is that shared? Can you see that?
Yes, you can see. Yeah.
Okay. I wrote the course for Repsol. Repsol allowed me the intellectual property rights when I was released. So I teach this course for my own benefit. Pore pressure is assessed by analysis of what we call impermeable rock formations. Now, impermeable is a time-dependent term as it applies to pore pressure analysis. You have some rocks that have virtually 0% porosity, zero effective porosity, therefore there is no fluid flow. However, there is fluid flow through a clay matrix. If there were not fluid flow through a clay matrix, as the porosity declines with depth, then the pore pressure would always be equal to the overburden stress, which we know not to be true. Flow rates in clay matrix is reference to geologic time. Formation flow rates reference to clock time are considered permeable, such as your reservoirs. The pore pressure of an impermeable rock has never been measured. Therefore, there are no standard measurements of pore pressure of impermeable rocks in specific conditions to compare and use as a reference. That is key. That means pore pressure, everything about pore pressure in a clay matrix is still in the scientific stage of hypothesis. Pore pressure assessment is accomplished by comparing available data to observations and using mathematical models and logic. The basic principle of analysis of pore pressure is the porosity decline trend with depth. Here, this graphic shows that a hypothetical decrease in porosity shows an increase in density, an increase in resistivity, and a decrease in sonic travel time. The equivalent depth method models relate pore pressure to the overburden stress and the effective stress. The effective stress is the grain-to-grain stress supporting the overburden, and the fluid pressure in the pore space is the pore pressure. The two combined equal the overburden stress in the models. The Terzaghi principle, the overburden is supported by pore pressure and the effective stress. The increase in pore pressure gradient will increase the proportional force applied by the fluid pressure, thus decrease the proportion of the effective stress applied, the grain-to-grain contact. When the proportion of pore pressure increases, then the decline rate, porosity decline rate, will decline. That means the porosity will not say it declines at 1% per 100 feet. When the pore pressure gradient increases, it will be declined at less than 1% per 100 feet. And we will pick this up on the logs and analyze the logs. The overburden, pore pressure calculation based solely on true vertical depth. Any calculation based on measured depth is not valid. A hypothetical normal compaction trend is assumed to be normally pressured. Normally pressured is hydrostatic pressure. Your formation water densities, hydrostatic pressure could be 8.9 to 9.0 pounds per gallon, about 0.44 psi per foot. Shale intervals are selected for analysis, and the resistivity of sonic travel time is used with the normal compaction trend put into a mathematical equation, and a pore pressure is calculated. Critical to the calculation of pore pressure is your reference height for the calculation. There are two normal reference heights used. This is an offshore work. You have your mean sea level and you have a depth. And you are most commonly, it's the drilling table where the flow line empties the top of the hydraulic column to the depth. Because these depths are different, the densities required to equal the pressure at a given depth are different. Here we have, this is the general equation. Rho GH, density times gravitational constant times height of the fluid constant. You have a MSL height is different than your RKB height. Therefore, your densities to equal this pressure here will be different. And doing the arithmetic there, rho A is greater than rho B, therefore. Now, the difference, when you calculate them, the difference between using a RKB calculation and a mean sea level calculation, there is a difference here, because the RKB calculation includes the height of the drilling floor and air. The density of air is significantly less than the density of seawater down to the mud line, and then you have your density of your formation being used in the calculation at that. This is the differences between the two reference heights. There are 7 processes every pore pressure model, pore pressure and fracture gradient model must complete to be valid. You first have to calculate the overburden gradient. Then you have to select your shale intervals, define your normal compaction trend, calculate your pore pressure gradient. Then you calculate an effective stress ratio or other fracture gradient model parameters. They have many different fracture gradient models. I am using the Matthews and Kelly model for a demonstration here. Then you calculate the fracture gradient. Then you calculate the permeable formation hydraulic heads. Those are the reservoirs that are the targets. And calculating the overburden gradient. The calculated overburden gradient at any depth is the sum of the effect of the gravitational force applied to the total mass above that depth. As depth increases, the density of formation is not constant. Most commonly, it increases. The overburden gradient is calculated by dividing the mass above the studied depth into discrete elements and summing that the product of the gravitational constant times the height of that discrete element times the density. I'm gonna here, often you do not get almost always you do not get measured density to the surface. Measured density begins at a certain point, usually below the surface casing, and often only in the reservoir sections. So you have to make some assumptions. There is work by Dr. Tom Miller that I reference in his shallow density profiles. And here he has 2 modules. One is near sediment source, like you're near the mouth of a river, and you're far from the sediment source. The difference between these two models is the sand content that is assumed, as opposed to your higher porosity clay matrix. And then in the calculation of the overburden gradient, there is a difference between these two. This must be understood by the pore pressure analyst, and he must justify his choice. When you do not have measured density and you have a sonic log or interval velocity, you can use a Gardner transform to calculate an assumed density. Here I display where you have density, sonic information through this interval, density only through this interval. You apply a Gardner transform and it matches, doesn't quite match right here. So the default parameters have to be changed. You have to fit it, and then you get a good match here. From this, you combine the shallow density and the Gardner transform and the measured density, and then the Gardner transform at the end. And that will give you a density profile from which you can calculate an overburden gradient. And here, using this, you calculated the overburden gradient here. Now, water depth has an effect on the overburden gradient given the exact same density below the mud line. If your water depth is, an example here, 4,123 feet using this same density, this is the calculated overburden. As the water gets deeper, the calculated overburden gradient will be less. This must be known, must be understood. Then you select your shale intervals. Most people commonly use the gamma ray log. And when you select shale intervals, there's a variance in the resistivities. I'm using resistivity here as an example. You can see that the resistivity varies. And if you use these discrete points to calculate, you get a non-uniform transition, and you don't know exactly where the pore pressure gradient rises above hydrostatic. It could be here, it could be here, it could be here. You don't know. So you use a scientific principle of statistics, put a moving average on it, and then you can assume using a moving average, it smooths this out to where you can much more readily determine where the most likely depth that pore pressure begins to rise above hydrostatic, that being right here. You must define a normal compaction trend. Pore pressure models take the difference between the observed log value and the normal compaction trend, put in a mathematical formula, and calculate a pore pressure. As the porosity decreases, resistivity will steadily increase and sonic travel time will steadily decrease. The trend in resistivity and sonic values in this hydrostatic pressure zone defines the normal compaction trend. That is the definition of normal compaction trend. It is the trend of a physical property through the normally pressured zone. Any physical property, density, sonic travel time, resistivity, through the normally pressured zone. A common mistake I see is people will do a sonic log on a linear graph. When I review a product and I see this, I return it. These are logarithmic relationships, and if you do this, some softwares will draw a point-to-point straight line, and then they will graphically match that to meet the definition of a normal compaction trend when the actual value is out here. This is invalid. So when you're reviewing a product, ensure that the analyst analyzed his sonic curve with a logarithmic scale and not a linear scale. Here's an example of erroneously created normal compaction trends. This one was created like this. This one does not fit the definition of normal compaction trend. Remember, the definition is the trend of a physical property through the normally pressured zone. And then here is this normal compaction trend here. I matched the physical property through the normally pressured zone. Now, this is a judgment call by the analyst because there are no pressure measurements here. A knowledge of the geology, drilling history is very helpful in this. Here, this can be discounted, this green line. This was erroneously created. This may be true. It's not implausible. The pore pressure gradient may be above hydrostatic up here. So you have to allow for that. That has to be considered a plausible solution. But the most likely solution is through this entire zone right here. And there it is. Your pore pressure gradient is hydrostatic until this depth, and it rises above hydrostatic. You calculate your pore pressure gradient. After you have established a normal compaction trend, you calculate your pore pressure gradient. They have different modules to do this. The Eaton module is the most widely used model to do pore pressure. It was developed in the depositional basin in the northern Gulf of Mexico, but it is applicable to any clastic deposition of clay particle size. Now, he developed two models, a sonic model and a resistivity model. These models I will show later are very similar. Now, it must be remembered that the default exponent for a sonic model is 3.0. That is default. That doesn't mean it has to be 3.0. Often in active depositional basins with extensive depth of deposition, I often use model at 2.6, 2.7, 2.8 works well for me. The default exponent for resistivity is 1.2. I have often seen a sonic model using the default resistivity model exponent. I have seen that very often. Here is what happens when you put a sonic model, a default resistivity model exponent, and a sonic model. This is a real well. Now, this particular well did not have a catastrophic event, but this pressure ramp exists over a wide area, and knowing this ramp is there, they still have blowouts. It exceeds 5 pounds per gallon in less than 1,000 feet. Now, in your pre-drill, if you do a pre-drill and plan your well, and the analysts mistakenly use the Eaton exponent of 1.2, you are 2,200 psi under balance when you hit this ramp. And suppose there's a permeable formation in that ramp, and you drill through it, and this is what you plan for. You have a major problem on your hands if that happens. When you are reviewing a product, make sure that that the analyst justifies the exponent he is using, or any model, the model parameters he is using for that model, because these are just default parameters. Default parameters seldom work to generate a model as precise as I'd like to see. This is the Eaton model. This is the formula for the Eaton model. If you notice here, you will see the shale resistivity divided by the normal compaction trend resistivity. It's the overburden gradient minus the difference between the overburden gradient and the normal pore pressure. Normal pore pressure, freshwater is 8.3454. Can you still see my share?
Yes, yes.
Yes, okay, because my screen changed. Okay, so I'm going to continue. Now, the overburden gradient minus the difference between overburden gradient and your normal pressure. Some formations are 8.6 pounds per gallon. 9.0 is not outlandish. I usually use about 8.8 unless I have a precise measurement. And then it's this difference times this fraction raised to this exponent. Remember, the default exponent was 1.2. Now, often log data is not available. When log data is not available, then there are assumptions the analyst has to make. And all assumptions the analyst make, he must justify. Here is the sonic travel time. If you notice, the fraction here is reversed. It's the normal compaction trend divided by the shale, where here is the shale divided by the normal compaction trend. The default exponent is 3.0 for sonic travel time. Now, the reason for this is you have matrix resistivity and you have water resistivity. The combination of the two give you your total, your bulk resistivity. The ratio of matrix resistivity to resistivity of connate fluid water is approximately 400. The ratio of sonic travel time and formation fluid water to sonic travel time and matrix is between 3 and 4. Sonic travel time of formation water, usually 189 microseconds per foot. Matrix, anywhere between 40 and 50, 40 to 55. So that difference between the matrix travel time and the matrix and the formation fluid travel time and matrix resistivity and formation fluid resistivity is the reason why the default exponents for these two models are so different. And here is an example using sonic. Now in sonic, you see perturbations in the log data here, a decrease in sonic travel time. This is most likely due to lithification. The gamma ray is fairly constant through here. A reasonable assumption is the formation chemistry does not change that much, yet the matrix travel time, the sonic travel time has a dramatic change here. So I exclude that from my model and I model just what I think is the non-lithified sediments. After you calculate your pore pressure gradient, then you have to address your fracture gradient. The model I'm going to demonstrate here is a Matthews and Kelly model. There are several fracture gradient models in use. I had to choose one. Matthews and Kelly is a very reasonable model. I've had a lot of success with it. The fracture gradient is measured by a leak-off test where the formation is fractured. This is a measurement. It can be used. The minimum horizontal stress measure after the well is shut in is you shut the well in, then the pressure relaxes, and from that you get your minimum horizontal stress. The minimum horizontal stress is not the fracture gradient. Normal geologic setting requires a force greater than the minimum horizontal stress to fracture the formation. You must defeat the strength of a formation to fracture the formation. When applying the LOT value to a fracture gradient, all rock properties are combined. That's the effect of the overburden stress and pore pressure and the strength of the rock. Like if you are at the same depth, if you are drilling an iron ore and drilling an unconsolidated sand, the fracture gradients in the two will be different due to the strength of the rock. Now, the Matthews and Kelly formula is very simple. This effective stress, what's called an effective stress ratio, K naught, is the key. Now, to develop K naught, you have a leak-off test. You know the fracture gradient at that depth there. You do not know it between here. But you know the pore pressure and you know the overburden gradient. So you have a measured fracture gradient here, 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 and here. So some assumptions you will make is that the fracture gradient is related to the pore pressure and overburden gradient. That is the relationship here. Once you, and from this, you develop your K naught. That's your leak-off test minus pore pressure divided by your overburden gradient minus pore pressure. These are the values calculated from these leak-off tests. Then you calculate your fracture gradient. Applying this equation, this is, and the pore pressure, it will calculate this fracture gradient. And this is what you will plan your well on. After you calculate your fracture gradient, you have to compute your formation hydraulic heads. This is based on what is called a centroid depth. The centroid depth is that depth in a dipping member, permeable formation member, where the pressure of the shale is equal to the pressure of the sand. The pressure of the sand, for example, I use 0.44 psi per foot. Shale, I'm assuming, is 0.6 psi per foot. That's what it takes to control keep the wellbore stable to drill to this reservoir. If you come 1,000 feet above the centroid depth, then your sand pressure is greater than your shale pressure. If you go 1,000 feet below the centroid depth, your shale pressure is greater than your sand pressure. And this is an example of calculating the difference. An example of well is drilled at balance. At balance means your mud weight is matching your shale pressure, and at a depth of 10,000 feet at the centroid. And I'm assuming 11.6 pounds per gallon. Pull that number out of the air. 1,000 feet above the centroid, the shale pressure decreases by 0.6 psi per foot, while the sand pressure decreases by 0.44 psi per foot. Now, if you calculate the pressures at the point 1,000 feet above, you're going to find that the sand pressure equivalent mud weight is 11.94 pounds per gallon. And while you were drilling, holding the shale stable, 11.6, then you will have a problem here. You're going to take a kit. This is something that in well planning, this must be known in well planning so that they can have contingencies for this. At 1,000 feet below the centroid, 0.44 psi per foot, then you calculate a pressure gradient in sand less than the 11.6. It comes out to 11.32. This is a graph. It must be known. You must take into consideration that although PSI per foot is linear, when you calculate a pressure gradient, it is not linear. I'm going to bring this up. And then this is a spreadsheet I developed. I'm going to change this density, fluid density, 0.6, good gas density. Let's change it to 0.5. See that shift? Now let's change it to 0.7. But if you notice, it is not linear. PSI per foot is linear, going to a pressure gradient. It is not linear. This must be known. Now, over what interval? If you're doing a short interval, then you can assume it's linear. But if you're going over 1,000 feet from your offset well, 1,000 feet difference in depth from your offset well to your prospect location, then you must take in, and using units of pressure gradient, you must take into consideration that that is not linear and it must be calculated. This is the end of my presentation. I did not quite make 45 minutes, and I would like to collect questions now. And if there is any clarification on any of the topics that I covered, please allow me to elaborate.
Okay, thank you, Mr. Chris, for this interesting presentation. I think that everyone enjoyed your presentation and the interesting information that we found. Actually, we have several questions. The first question is saying, why we don't use the TVD-SS as reference instead of TVD, because we may have different in kilipushing.
The pressure is referenced to a vertical depth. If you have, say, a deviated well, and you drill down, say, a horizontal well, you drill down to 8,000 feet, and then you drill horizontally 5,000 feet. If you use measured depth, you are still at the same depth, true vertical depth, and your geologic environment has not changed. If you use measured depth, you are still at the vertical depth, the same pressure horizon, so your calculations will be wrong if you use measured depth. Say you got 12,000 feet, 3,000 meters measured depth, but 1,000 meters true vertical depth, your calculations must be with true vertical depth. You can, nothing, the pressure will not change as you drill further with measured depth, but if you use measured depth in your calculations will change when the pressure actually has not changed. So you must use true vertical depth.
Okay, thank you. The second question is saying, at what depth from seabed I should stop Miller and step to Gardner?
Okay, can you state the question again, please?
Okay, at what depth from seabed I should stop Miller and step to Gardner?
I'm sorry, I'm not understanding. Did seabed?
Yeah, I think that he is asking about the depth when we shift from Miller to Gardner methods.
Okay, yeah, when we shift from Miller to Gardner, okay, using now here you shift from Miller. Okay, you match Miller. Now Miller has parameters. The Miller shallow profile has parameters you can vary, just like Gardner. So you want to match the technique I use, because I actually know Dr. Tom Miller. And I've had lengthy discussions with him about this shallow density. And on some issues, we have a little disagreement, but not much, just very, very technical. But I match the Gardner to his density, to his algorithm in the shallow part. And where I have density data, measured density, I match the Gardner there. So those, an assumed shallow density profile based on the research of Dr. Miller and a measured density based on actual measurements. Did that answer the question?
Okay, thank you. The third question is saying, are these models and equations are valid for carbonate reservoirs as well?
Yeah, no, these are not carbonates. This, as I stated early, pore pressure, these models are for impermeable, what's called impermeable formation. The reservoirs are governed by hydraulic head. So these models cannot be used in permeable formations. A model must exclude permeable formations. Then to assess the pressure of a permeable formation, you must use the centroid concept. You may have measured in offset wells a measured pressure, and you seismic can tie this formation to your prospect location. Then you can use the centroid concept to predict the pressure of your reservoir at your prospect location, assuming connectivity.
Okay, thank you. So I have another question. How can we have a compaction that which is the fluid explosion from formation and in the same time normal static pressure?
You can have it. That is a particular part of the course that I wrote where I actually define the forces that create a pore pressure increase. As if there is not resistance to flow, fluid, the water flows through the shale. If there is not sufficient resistance of fluid flow to prevent inviscid flow, then the pressure gradient will remain constant. When there is resistance to flow sufficient to prevent inviscid flow through the aperture from one pore space to another, that is when you have a pore pressure gradient increase. If where the clay-sized particles are very shallow, the connections between pore spaces is very large. There is no resistance to fluid flow as porosity decreases.
Okay.
At a certain point, the opening between the pore spaces decreases to a point to where even this small flow, there is resistance to flow, and inviscid flow cannot be achieved. That is where the pore pressure gradient increases.
Okay, thank you, Mr. Chris. Another question, how to adjust or optimize Eaton exponent?
Say again, please.
How to adjust or optimize Eaton exponent?
Oh, there, if both doing pre-drill work and real-time work, you have other observations. And pre-drill work, you're looking at drilling reports from your offset wells. You're seeing the details of what happened while they were drilling. If you're doing real-time work, then you're seeing the weight on bit, you're seeing the rate of penetration, you're seeing the gas return, and your model must be adjusted to match your observations. Now, you're always going to get a certain amount of gas, but then when that trend in gas changes, something caused it to change. It could be an increased pressure, or you may have penetrative formation that just has more gas to give up. If your weight on bit is constant and your penetration rate increases, there has to be a reason why it does that. It could be a formation change, or you could have gone into an underbalanced condition. And the hole is actually helping drill itself. The D exponent model is tuned to that. But this is a very nebulous science. All these observations have to be put together, and the analyst has to logically deduce some conclusions and then adjust his model to that. I have a course where I teach analysts methods to apply this logic. Pore pressure analysis is complex. It is very subjective, and it is a nebulous science. But everything that the analyst does must be consistent with the observations.
Okay, so the last question that we have, why the fracture gradient from the leak of test is always overestimated?
When it is greater than the overburden, is that the question?
The question is saying why the fracture gradient from the leak of test is always overestimated. Why is
it always overestimated?
Yeah.
It is. I have seen it often underestimated.
Yeah.
I would have to offer an answer. I'd have to look at specific projects and then make a determination. But very often, my observation is I find that the calculated overburden gradient is insufficient. That is, I see that, and it is usually low. If the overburden gradient is low, then the fracture gradient will be lower, will be estimated lower than what it actually is. If the overburden gradient is too high, the fracture gradient estimate will be too high. But to answer that, I would have to look at the specific model, the specific project, and do a very detailed analysis. Now, he used the word always. I would have to go into, always means there's more than one analyst involved. I would have to review the methodology that is being used. The fracture gradient is very seldom have I calculated a fracture gradient that was exactly what they measured. Very seldom. There is a range of uncertainty, but I can get close. Pre-drills have a wider range of uncertainty than real time. But I would have to, was the question, why is it always overestimated?
Okay, thank you, Mr. Chris.
Was that a sufficient answer?
I think that the person that asked that question, I think it's sufficient for him, I think. Yes, he answered the clear. Thank you, Mr. Chris.
Okay, thank you.
Okay.
That's a very good question. That is one to where if you review products or use products, you have these observations. There are certain trends that you will observe, but that is, I was glad that question was asked.
Okay. Thank you, Mr. Chris, for this interesting presentation. Everyone enjoy it, and also we got a very, very, very good and perfect feedback from the attendees into the Zoom chat. I think that they benefited a lot from information from this webinar. Thank you again for your effort and time to prepare this interesting presentation.
Okay, I want to thank you for inviting me, and I want to thank everyone that attended. for the attention. And if there's, please make note of my email address. And should there be any concern, question that you have, feel free to email me. And I want to thank Reservoir Solutions especially for giving me the opportunity to present this. I thoroughly enjoy pore pressure and fracture gradient modeling. Although it is very demanding, it is enjoyable to me, and I enjoy sharing my ideas and my knowledge. Thank you very much.
Thanks again, Mr. Chris, for your time and effort. And also, very big thanks for the attendees for our today presentation. And please, if again, I wanted to remind you, if you wanted to get a certificate for attendance of this webinar, you can fill into the form that its link was sent into the Zoom chat, and I will send it again now. Also, I wanted to remind you of our two upcoming courses, the practical seismic interpretation and the well killing methods. You can enroll into the two courses and have a discount. And also I will share the links for the course content and also the registration link. Also, you can follow our Telegram channel and our LinkedIn profile and page for the upcoming courses and the webinars. Thanks again, Mr. Chris, and thanks everyone.
Okay, thank you.
Thank you.